much for coming to our seminar, to the seminar of group of campus, in particular della Università Nazionale de Colombia della sede di Bogotà. Today we have the pleasure and the honor to have with us Dr. Giulia Isabella. She's postdoc at UCLA. She did her PhD in Orsay, in Saclay, and the master degree in Lausanne. She's a great expert in the causality constraints and positivity constraints from causality. So she will talk about today about the massive gravity is not positive. So thanks again, Giulia, and welcome.
Okay, so thank you so much for the invitation. I'm gonna tell you a bit about this paper that now came out almost more than a year ago, but I'm glad to see it's still some interest. So this work was done with Brando Bellazzini, who was my PhD advisor. Sergio Ricossa is the student of Francesco Riva, who's a faculty in Geneva. And so as you can tell from the title, I'm going to talk about positivity constraints in the context of massive gravity. And please feel free to stop me at any time if something is not clear or if you have any question or I'm assuming something that is not familiar with. So before getting into any details, I wanted just to start by telling you what the philosophy of positivity constraints is, in case you're not familiar with it. And the idea is quite simple. So if we are, let's say, in a space, a two-dimensional space, and then we put the energy of our interaction on the vertical axis, and on the horizontal plane, I'm going to put like every possible theory, okay? And we could select, for instance, like some subspace of high energy theories, which could satisfy a certain type of principles. We could pick, for example, string theories or like theories that satisfy unitarity and causality or some certain assumptions about the UV. Okay, this is like what I'm going to call the UV, very high energy. And then we can like run down this theory through some RG flow all the way down to low energies, okay? And in these low energies, this will select another subspace of what we call the effective theories, okay? So this is gonna be like EFTs, effective field theories. And the question that positivity wants to answer is basically, given some set of assumptions, the UV, which will be the boundary on this effective theory? So which are the effective theory, low energy, that is consistent with a certain type of UV completions. Okay, good.
Sorry, probably I did something bad. I cannot hear you anymore. What I did?
No, it's my fault. Sorry,
Okay.
I clicked or something. Sorry,
Okay.
sorry. Now it works. Okay, good. Okay, so good. Okay, so the idea basically of this paper and some papers before ours was to put some positivity constraints on the context, in the context of massive gravity. Now, massive gravity is like a deformation of gravity or Einstein's gravity in the IR. And originally it was the idea was the following. So we add a tiny mass to the graviton, which like it's massless in the theory of Einstein's gravity. And basically, like everything looks massless at short distance, and it looks massless all the way to the Hubble scale. And at some point, the mass will kick in, and gravity becomes like a finite range force. And this is a way to explain inflation, basically. So not inflation, but like the accelerated rate of the universe. So this is kind of like the original idea. And I mean, there has been, I think, more than 1,000 papers written on massive gravity in the last 15 years since it was, the equations were written down. And a lot of phenomenology has been studied, and I'm not an expert in all of that, but I wanted to just give you like a few facts about it that are necessary to understand what I'm going to talk about later. So let me start just by telling you a few facts about gravity as an effective theory, and then we're going to add the mass and see what changes. So in a standard GR, you know that we can write an action that looks like something like this. Okay. And the standard way to compute the amplitude from that is to linearize g mu nu, the metric, and then into some eta mu nu plus corrections. And this correction, this perturbation is we call it the graviton. And this is a spin 2 particle with 2 degrees of freedom. Okay? And you can compute amplitudes for it. It comes with some polarization tensor, which has 2 indices, and yeah, it has a spin 2. Now, at this point, you can compute amplitudes with it. For instance, you could compute HH into HH. H is my graviton. Okay, so 2 to 2 scattering of a graviton at 3 level. And this amplitude turns out to scale in this way. It goes like S over m Planck squared, where S is the center of energy, center of mass energy squared. Okay, so what does this amplitude tell you? It tells you that if you go to energies above m Planck, then the amplitude is going to become order 1, and then the probability is larger than 1, and the Yotta effective theory breaks down. This is what we call the strong coupling scale, okay? So what this tells you is that this theory of gravity, if we put like a line with all the possible, let me work in distances, we can use this theory of gravity all the way from 1 over the Hubble scale, so all the way from like the size of the universe down to 1 over m Planck. Okay, the Planck length. And in principle, we have predictive power, let me put the line here, all the way from here to here. Okay, we can use this theory to make prediction, compute amplitudes, even though it's not UV complete, but we can still do our calculations. Good. Now, what happens if we decide to add a tiny mass? Okay, so we start from the same action, and this time we add a little mass with a potential. Okay, this is the standard deformation that people usually consider. So as soon as you add a tiny mass, what happens to the graviton is that the number of degrees of freedom immediately changes. This theory is very different than the one that we started with. You know that if you have a spin S massive state, this comes with like 2s plus 1 different degrees of freedom. So in particular, for a spin 2, we're going to end up with 5 degrees of freedom. And it turns out that if you compute the amplitude, in particular for the longitudinal ones, the ones like a polarization 0, 1, -1, the middle one, they were not there in the original case, those tend to grow fast with energy. Okay, and you can think of these as like some Goldstone bosons. They always appear with some derivatives, and since they have derivatives, they grow faster with the energy. So it turns out, so you can compute these amplitudes for a generic potential, and then you can start tuning all your parameters to try to have a growth in energy that is as slow as possible, okay? Because you want your effective theory to be valid for a large range of scales. And it turns out that the best you can do is actually something that goes like S cube over some scale. Let me maybe just erase this, okay? Okay, so S cube over some scale that we usually call lambda 3 times a function of 2 parameters. Now these are like scalars, like Wilson coefficients or parameters. They usually are called the C3 and D5. This is just like historically. And this lambda 3 scale is given by the mass squared times m Planck 1/3. Okay? Okay, so now we can ask, okay, what is the validity of this theory? Where can we use this effective theory safely? And so first of all, we want the mass to be very small because it has to be consistent with what we observe in our universe, okay? So we want the mass to kick in only when we are basically at the Hubble scale. So let's start by saying that 1 over h0 should be more or less 1 over m. This fixes how big m is. By the way, there's also like some experimental bounds on m from gravitational waves, which is like something around 10 to the minus 22 electron volts. So it's like really tiny. We're talking about a very tiny mass. And we can go all the way to 1 over this lambda 3, which is the strong coupling scale. Okay, so we have reduced the validity or effective theory here. So, and if you pick m of the order of h0, this lambda 3 is something around 800 kilometers. So it's, like our validity or our theory of gravity now goes from the larger scale of the universe all the way down to 800 kilometers, which is much worse than what we started with. And you might say, okay, but this is not a very good theory. And what people have really worked hard on is to basically, there's like some mechanism, which you might have encountered, it's called Weinstein mechanism, which basically tells you that if you're close to a compact object, then you're going to start feeling the effect of gravity being strong, right? Because the assumption that we made at the beginning that is basically Minkowski plus little correction is not valid if you're like on the surface of Earth, because then you see like really like the strong coupled effect of gravity. And this strong coupled effect of gravity actually can mask, the effect of this little mass. So somehow people have some ways of pushing this way down by considering strongly coupled effects. But from the point of view of the effective theory, this is like what our strong coupling scale is. And the question we want to ask is basically twofold. So first of all, what does positivity have to say about this C3 and D5 space? Okay, can C3 and D5, which are free parameters, take any values if we want the UV completion to have certain properties? So the first question is, what are the bounds on C3 and D5? Okay, from positivity, which we're going to see in a second what this looks like. And the other question is like, okay, so lambda 3 is the strong coupling scale. This is like the worst case scenario where like your theory really breaks down. But like you expect new physics to enter somehow before that and kind of correct this behavior and give you a better behavior that allows you to go at lower energies, or higher energies or lower distances. So the question is, what about...
Of course, everything here is in a flat background.
The amplitude, yes, we're going to consider flat background. Yeah, I'm going to lay out the assumptions in a second more precisely, but yes. So somewhere around here, there is a scale which is going to be really the new physics, okay, the scale of new physics. This is the cutoff of the effective theory, which might coincide with this one, but it's really like the moment where you have to introduce some new particles, some new physics, they will combine and give you a better behavior, okay? So can we say something about the cutoff from positivity constraints?
So I don't understand really the difference between lambda and the lambda 3.
Yes. Okay, so let me repeat. So lambda 3 is the scale. So when you take energies, let's say when the energy is order lambda 3, then the amplitude is order 1.
Okay.
Okay, so this is a strong coupling scale. You get there, then probability becomes larger than 1, and then you break unitarity, and then it's like, okay, you have to throw away your effective theory. But in principle, this is like really like, how to say, like the dimensional analysis prediction of where your cutoff is. But then like, it doesn't mean that new physics will appear only there. It can appear earlier. Okay, so what I say by lambda is really like the mass of the new state that you have to introduce in your spectrum or that you have integrated out. Okay. Any other question? Okay, so this is the goal. And okay, so this is the theory that we want to bound. Let me just tell you a little bit about the positivity constraints and how we're going to actually put bounds in practice. And to do that, let me start by making a list of all the assumptions that I'm going to make about the UV, basically, what I want the UV to satisfy, okay? So first of all, I'm going to consider Lorentz invariance theories. This is a big assumption, okay? So if you're happy to get rid of that, the rules of the game change completely. And some attempts have been made putting positivity bounds on theory with broken Lorentz invariance, but weird stuff happen with crossing, with the analyticity. So I'm not gonna go there. I'm gonna assume Lorentz invariance all along. And so Lorentz invariance, we know what the asymptotic states are. We're gonna work in flat space time. And the object that we know how to deal with is the scattering amplitude. So I'm gonna call M my scattering amplitude. Tell me if I write too small, okay, in case there's
No,
any problem. It's good?
visible.
Okay.
It's visible. Yeah.
Okay, maybe a little bit. Okay. So my amplitude M, and now what the amplitude we're gonna consider is scattering of 4 gravitons, okay? 2 to 2, also because higher points, we don't really know what's going on. So each graviton has some polarization. We said there are 5 degrees of freedom. So each leg is going to have an extra label. So we have lambda 1, lambda 2, lambda 3, lambda 4, which run from -2 to 2. Okay, there's 5 choices of them. And it's going to be a function of S and T, where these are the Mandelstam variables. S is P1 plus P2 squared, and T is P1 plus P3 square, if everything is incoming. Okay, this is the first assumption I'm going to make. Next, I'm going to consider unitarity. Okay, so this is just a statement that my S matrix is unitary. So S dagger S is equal to 1, and this translates in a constraint on the amplitude itself, which is of this form. If you replace S dagger with like 1 plus IM, M dagger. Okay, I hope I got the daggers right. So what does this tell you? So basically this tells you that on this left-hand side, it's an imaginary part of an operator. And so as soon as you have, as soon as this thing is non-zero, you develop an imaginary part. So what does this look like if I want to draw a line and stay in the space of S, okay? This is like energies. So if I'm above a certain certain threshold, okay, which is basically when you start producing particles, it turns out that this imaginary part is non-zero. And this can be written down as some branch cut in this space. Let me maybe color this. So if you go at energies above a certain amount, unitarity tells you, okay, now there's an imaginary part, which is constrained by this expression, and then there's going to be a branch cut. Okay, next, crossing. So crossing, I'm sure you've met this already many times, is basically the statement that what happens if you exchange 2 legs. So if you take leg 1 and 3 and you exchange them, you're going to flip S and U, the 2 Mandelstam variables, and the question is like, what amplitude do you land on? And it turns out that like crossing tells you that these are 2 boundary values of the same functions. The same function describes the S channel and the U channel. So in particular, we're going to have the S channel will appear as another branch cut, this time at negative energies, okay? And the crossing tells you how like basically the discontinuity on this side is related to the discontinuity on the other side. And we're gonna see more in detail how this exactly looks like. But let's continue with the conditions. Next, causality. And what I mean here is microcausality, which is the statement that 2 operators, which are space-like separated, commute. Okay, so this is a statement at the level in momentum in position space. Now, if you take this statement and you Fourier transform it to momentum space, and you see what does it imply in for my amplitude, it turns out that it tells you that basically all the non-analyticities in this complex plane, okay, we can see energy as like a complex variable now, they all lie on the real axis. So the upper plane and the lower plane are basically analytic in the energy. Okay, this is like, I don't know, it was worked out in the 50s, 60s, and it's like a lot of very mathematical papers. And there's like some challenges on how to exactly get all this region, but usually that's the statement, okay?
Of course,
Okay.
one does perturbation theory, and at fixed order in perturbation theory, spurious singularities appear like cuts of the of the Feynman integrals that one is involving.
So cuts of the Feynman integrals will give you these cuts. They should be like all on the real axis. Like I don't think we have any example in perturbation theory of non-analyticities appearing in the upper or lower plane.
Of course, they are artifacts of the way in which one truncates the series. I mean, the general principle that you are expressing bring to this picture, but
Like what type of
at a fixed order, I mean, something else can appear, but then in the resummations or in the way of treating the full amplitude.
You mean like if you separate in like different diagrams?
Yeah.
You see like some diagrams. I'm not sure. Like what I'm thinking about is like I don't know everything like this. You cut it, you get real energies like above the mass of the energy you need to produce these two particles. Then you get an imaginary part. I don't know, more complicated diagrams.
I mean, involving
Yes,
boxes and stuff more complicated.
Yeah.
I mean, but they are, however, artifacts of the way of doing perturbation theory, of the way of doing tensor reductions and separating the
I'm not sure. I don't have an example in mind where you actually cut a diagram and you get a cut here. I don't know any example of that. But yeah, in perturbation theory, once you have your full amplitude, this doesn't happen. There's no examples of it. And the claim is that this is valid at all energies, even if you're beyond perturbation theory. Because in particular, if you're like high up here, at some point, the perturbation theory breaks down. You're like in a strongly coupled regime. But the claim is that this analyticity property is valid even beyond that. It's valid. It really comes from like a property, a microcausality property, which is non-perturbative.
Yeah, they are general principles.
Exactly. Okay, so at this point, we have a plane. We know where the cuts are. The natural thing to do is to start drawing some contours. Okay, so the standard contour that is usually drawn in this context looks like this. Some kind of like semicircles which close. Okay, closes. Okay, and now you can see immediately now this contour doesn't enclose any non-analyticity, so the integral over the whole contour must be 0 by Cauchy theorem. And what we can do is basically separate it in 3 contributions. So the integral over the small circle, which is this guy in the middle, plus the integral over the branch cuts, which are the 2 guys on the sides, plus the integral of the big circle. This should sum up to 0. Okay? Okay, so the last ingredient that we need is something that I'm going to call polynomial boundedness. This is like a statement from this usually assumed in axiomatic quantum field theory. It's like what type of distribution can we have in position space? Now this constraint, which is like nothing crazy, okay, combined with unitarity, has been proven to imply something that is called the Flusser bound. Are bound. It's only one. Oops. Flusser bound. Which is the following statement. If you have your amplitude...
And also the cluster decomposition principle brings such a form of the interaction. No?
Yes, I think so. Yeah. Okay, so if you take the amplitude, we divide it by s squared, and we take the limit of s going to infinity, the modulus of s going to infinity, then this vanishes. Okay, so this is like a statement on the growth of the amplitude at large energies. Okay, and this can be proven by basically partial waves. You have to play with this a little bit, but it's really nothing hard to prove. And so this tells us that if we take our amplitude, we divide it by something s to a certain power, which is larger than 2, then the circle at infinity will not contribute, will go to 0. Okay? So basically this contour that we drew gives us a condition between the small circle and the contribution from the branch cuts. Okay?
This is the analogous of the subtracted dispersion relation.
Exactly. This is like, exactly, it's not analogous. It's exactly that. We're looking at, this is like a dispersion relation, and those divided by something is called subtractions, and that's what you get. And basically, the idea is the following. Now, the circle at low energies, you see this is a circle close to the origin, so it's a low energy contribution. And this is something that is valid in our effective field theory. So this we can actually like compute explicitly within our effective theory. We can use perturbative methods. We can use like everything that we know. Then we have a contribution from the branch cuts. The branch cuts will go all the way to infinity, and those will contain all the new physics, all the stuff that is mysterious and we don't know about it, is the UV completion effects. We don't know what it is, but we know that it should satisfy some of those properties, or so satisfy those assumptions that we made. So in particular, should satisfy this unitarity, which ends up being what gives you something positive. Okay, so that's where positivity comes from. Okay, so
the effective field theory is in the small circle, and the UV completion is in the cut.
yes. And a big circle goes to 0, and we can throw it away because
goes to 0 of the
exactly.
because of the subtraction.
Exactly. Good. Any other question?
And of course, one can subtract, but also if one simply dimensionally regularize, should again get that the big circle goes to 0. Because I mean,
Yes.
what would impede to go to 0 would be the UV divergences, but if they
Yeah,
are
so here we're talking about
regularized, I mean, they should also go to 0. But
yeah, I
however,
mean, we expected like
is another way of doing this this subtraction.
yeah, so this is the physical amplitude. So like if you go like high energy, you have to like regularize your divergences, your coupling will run, so they will have the coupling at that energy. We expect that at some point the UV completion should be, you know, doesn't have any divergences. So like up here, I think that's, and also we don't compute anything explicitly up here. So
yes, because they go to 0.
Because it goes to 0, yeah, which is like a statement from like axiomatic Gottfried field theory. Okay, good. So let's see how we can apply this to our theory of interest, which is, I didn't say that, but like the theory which depend on these two parameters, C3 and D5, that I was telling you below before about, is called the RGT. Okay, so that's something that's usually, that's like the most common massive gravity theory, okay? Okay, so what we're gonna do is define what I'm gonna call an arc. Okay, so this is the integral over the small circle. Okay, and I'm gonna take basically this combination of amplitudes divided by something that goes like s cubed. Okay, this is just a choice I'm making, which turns out to be practical. Now, let me just tell you what I mean by this guy here. So I simplify this a little bit. So when I put two indices, it's because I've chosen the first and the third particle to have the same polarization, and the 2 and 4. So basically, we are elastic in polarization. The in and out is going to be the same. You can do it without this, but it turns out that like the most similar the in and out states are, the easier it is to put positivity constraints. And for us, this was enough to get the bounce that we got, and we're happy with it. So that's what we focused on. So this is like elastic in polarizations, okay? Okay, so the standard way of putting positivity constraints is in a particular regime, which is t equals 0. t equals 0, t, you know, is connected with the scattering angle. So if you go t equals 0, it means that the states basically go in a straight line. They go in and go out in the same direction. And so let's see what happens when t equal to 0. So we have lambda 1, lambda 2 of 0. So the arc here on the small circle is something that we can compute explicitly. Okay, we can do the 2 to 2 amplitude for massive gravitons. This is, you can either get this from the Lagrangian that I wrote earlier. You can do this on shell by like computing all the possible structure. This is how I did it. And then you can fix all these free coefficients in order to have a softer behavior at large energies. But this is something that you can do in practice. Now let's see what is the contribution from the branch cut, okay, which is the one that is more, that we need to work a bit more on. Okay, so this circle, again, you can open the contour and then you get two contributions. One, let me just show you. One is going to be at positive energies from the S channel, and the other one is going to be from the U channel, okay? So we're going to have two contributions. One is going to be from, so 1/2. I'm going to pick where, basically I'm going to say, okay, everything I can compute up to a certain cutoff, okay, lambda, and inside I can do my EFT, and outside I'm going to need new stuff. So basically I'm going to start it at some lambda, okay, which this is the thing that we want to bound, okay? Okay, and then the integral goes all the way to infinity. We have ds over 2 pi I, and now the contour goes around the branch cut, so we're going to have basically amplitude plus I epsilon minus amplitude minus I epsilon, and this gives you a discontinuity. So this is a disk of lambda 1, lambda 2 of Sn0 plus the discontinuity of minus lambda 1, lambda 2, Sn0 divided by this particular subtraction plus 0 cube. Okay, this is one contribution. There's another one. And here again, I have some freedom where I basically put my circle, and I'm going to pick it to the crossing symmetric point because it's going to be simpler later. I'm going to choose this. That's where I put my circle over 2 pi I, and then we have the exact same story. Lambda 2 of S0, and then the disk of the other one. Okay. Now, so as I said, the goal is to apply unitarity to this, but unitarity is something that is valid only at like positive energies, okay, in the physical regime, where actually you do you compute the amplitude, and it's like a physical process. So the idea is basically to use crossing to bring the left hand side cut to the right. Okay, so the channel want to use crossing to bring it to the other side. Okay, so for this I need to tell you a little bit more about how crossing works. Okay, so in general, when you take, what we're going to do is crossing S and U, okay, because that's what we need to bring the left cut to the right. And the rule in general looks like this. So you have an amplitude on the U channel. This is going to be equal to like a big matrix times the amplitude on the S channel. Okay?
We cannot see what you are writing.
You cannot see what I'm writing.
Okay. No, yeah, I see.
Sorry. Maybe got stuck. Okay.
No,
okay.
I can see.
Okay. So this is like a big matrix. So this is going to have some, lambda 1, lambda 2, lambda 3, lambda 4, and then lambda prime, etc. And this is going to have lambda 1.
Okay.
So basically the statement is that if you flip two legs, you're going to mix up all the polarizations in general for a massive state. Okay? This X is a string of something that's called Wigner-D matrices. We know what they are. They're a bit annoying. We'd rather not work with them. But yeah, I mean, we know what they are. Okay? We know their properties. Okay.
A little group. Coming
it's little group. Yes, massive little group. Okay. Now, there is some... So in particular, if you want to take the left channel cut, I don't know why it's not working this anymore. Yeah, I don't know. I'm pointing, but it's not working. Okay, this guy, this left channel, the U channel cut and want to bring it to the other side, then we need, if we do that, we're going to end up mixing all the polarizations. So in particular, for a spin 2, there's a lot of combination. There's something around like 70 amplitudes that you need to use. And this is like very annoying. But thankfully, there is a
Of
particular
course,
regime.
things would have been much more easy at t equals 0.
Exactly. So indeed, that's what I was about to say. If you go to t equals 0,
Which is the case that does the Pesach in the book.
yes, I assume. Yeah. Okay, so if you go to t equals 0, the amplitude of u and t, or to u and 0, sorry. So for lambda 1, lambda 2, let me say take the elastic one, goes to just like m of minus lambda 1, lambda 2. Okay? So you just have to flip. This is true, by the way, also for massless particles. Crossing is much simpler for massless particles. Just flip lambda in minus lambda, okay? Good. So since we are now at t equals 0, we can apply this. And basically, it's a simple, okay, we can do a change of variable, which sends something like s prime is equal to minus s plus 4m squared to go from s to u. And then we use the property that I wrote before, so that the discontinuity of m of u becomes minus lambda of s, okay? So we do let me repeat it once more, maybe it was a bit fast. So we start from, change of variable, then this disk becomes disk of u, this s becomes a u, and then we can use crossing, and you recover basically that the whole second line is the same as the first line. And so the one half cancels, and you just get one time this contribution, okay? It's like a one-line exercise that you can do very easily. Okay, so what we use here is basically crossing. Okay, so at this point we have, so it said one half sums, and then we get twice this guy, ds over 2 pi I. And what I'm going to use now is unitarity. So the discontinuity around the branch cut is equal to this imaginary part of this function. And we know that the imaginary part is constrained to be dagger. So let's see if I... Yeah, I don't know why my pointer is not working. It's dagger, okay?
Yeah, we can see.
Okay, so what I'm going to do is just replace it. So in particular, the discontinuity of m lambda 1, lambda 2 is going to be something like 1, the state 2, m dagger m, 1, 2, plus 1, 2, m dagger m, minus. Okay, so 1 and 2, I mean the momenta. So since t equals 0, we have the P3 is equal to P1, okay? Divided by s minus 2m squared cube. Okay, so here you see clearly that this structure is a square of something, right? Is lambda is 1, 2 m dagger times m 1, 2, and so this is the square of something, and since it's a square of something integrated over something positive, this whole thing is positive. Okay, end of the story, this guy is positive. Okay, so this is something that we get from the properties of the branch cut. Okay, I didn't impose any physics here, it's just like general properties of the UV. Okay, so conclusion of this step, we basically saw that the amplitude at t equals 0, or this arc, this IR arc at t equals 0 must be positive. Okay, so what does this mean? So let's see. So we can compute this arc at t equals 0. Let me maybe put here t. And then take the limit t equals 0. And it turns out that it has this form. Okay, this is something that you can do with some scattering amplitude techniques, as I said, or whatever, Feynman diagrams, whatever you like. And you get a function of C3 and D5. This is something they can compute explicitly. I'm not going to write it down. It's just some like linear combination of C3 and D5. Okay, there is a different condition depending on lambda 1 and lambda 2. Okay, so this is like a set of inequalities. Okay, so in particular, you're going to get for 0, 0, longitudinal scattering from 1, -1, 1, 0, and all this combination. Usually it's the longitudinal ones that give you the good conditions, okay?
They are
And then,
Helicity amplitudes.
sorry?
They are Helicity amplitudes.
Yeah, exactly. Different choices of the polarizations. Yeah. And that gives you some inequality, and then you can make a plot out of it. This is my hand version of that, but if you like, this is in our paper. And it turns out that the thing that you get looks like a potato like this, okay? So everything that is inside the potato is consistent with this positivity constraint. What is outside is excluded, okay? And these values range, I mean, this is something like 0.15, like there's some numbers attached to it, okay? It's small values. So what does this mean? It means that if you want to have an effective theory that is consistent with all these UV properties that I mentioned, your parameter, the numbers that you put in for C3 and D5, which were completely unconstrained where we started, actually have to be inside this island. This result was already found in this paper by Chung and Remen in 2016. And yeah, by basically imposing
this is at t equals 0.
At t equals 0. This already you get something that is very constrained at t equals 0. Okay? So this is already tells you that there's like very small space left for these theories to be alive. But since then, a lot of more papers have been written on massive gravity. So we were like, okay, can we do better and find even more constraints? And something that is easy to imagine is like, okay, t equals 0 is literally things going on a straight line. Okay, so there's so much more richness and physics beyond that. So can we go beyond that and still put some bounds? So let's try to do this. Okay, let me go back. Okay, so now we're gonna try to take t different from 0 and see what goes wrong, what problem we might encounter trying to do that. So first, crossing, as I told you earlier, becomes much more complicated. So this, I know some people who actually try to work out the numerics for a spin 1, and you have, tens of amplitudes to deal with. It becomes a numerical problem. It becomes really a pain to work with. So like it's doable, but it's complicated, especially if you want to go higher in spin. So already spin 2 is 70s, or amplitude, etc. The second problem, here I didn't write it, but we use unitarity. It's even more serious, and is the fact that now we're not at equal 0. So P3 is not equal to P1 anymore. It's not forward limit anymore, okay? So here what we have is going to be something that is like 3 lambda 1, 4 lambda 2, okay? And this, you see, immediately is not the square of something, is not positive. Okay, so the positivity breaks down immediately, okay, as soon as you move away from t equals 0, the simple positivity. Okay, so let's try to, I'm going to show you how we fixed these problems. So as I said, now we're going to put a t everywhere. So now it's amplitude of t.
I mean, the problem is that you lose the positivity.
You lose the positivity, and yeah, and there is the challenge of crossing. So, okay, can we still find some bounds that can give us some, constraints? Despite those two problems. Let me just tell you how we tackle these two problems. So, crossing. Let's start with crossing. So, as I said, here there's like t's everywhere. And if we want to do a change of variable to bring the U channel cut to the S channel, we're gonna have all this X matrix that I said earlier. And so this guy is gonna appear and ruin a bit the game. But there's actually a different limit if you think about it for a second. If you are at very large energies and a very large t, if all your Mandelstam variables are very large compared to the mass of the guy, your amplitude effectively is going to look like a massless amplitude, right? If S and T are, if you take your amplitude, you expand a very large S and T's, it's the same as expanding at M equals 0. So somehow there should be a limit where these Mandelstam variables are large, where it reduces to a massless case, and the massless case crossing is very simple. Okay, so this is the idea. So what we're going to do is basically choose a regime. So let me move this a bit down. A regime of T, which is going to be, between, let me say, it's going to be smaller than S, so in the physical regime, larger than M, where basically crossing takes this form. Lambda 1, lambda 2 of U and T is equal to M of minus lambda 1, lambda 2 of S and T, plus some corrections. The scale like this. So you see, when I take the mass to 0, I recover the usual crossing. When I take T to 0, I recover the usual crossing. But in general, I have corrections. And now it works again. So now the corrections is something that we know what the Wigner D is. So we know what the corrections are. So we can actually compute them and check how big they are to make sure that our approximation is good. Okay. So that's the limit we're gonna take. So
I mean, in this regime, the Wigner factors does not affect anymore. Became just phases.
Yeah. So basically, in this regime, the
I mean,
X
like
matrix
it's like a massive, a massless theory, and so
exactly.
the factor of the little group are just phases.
Exactly. So you're gonna have basically this big X matrix is gonna become a diagonal matrix plus corrections. So the more you move away from the diagonal, the more of these factors correction you're gonna pick up, but you have those under control because we know what the matrix is. This is like a trick to simplify our calculation and do it by hand without a big computer. Okay. So in particular, as I said, what the regime we're gonna take is T. We're gonna be below the cutoff, okay, because we're gonna still be, within our effective theory, and M squared. Okay, so as I said, then we can apply basically crossing in the same way as we did earlier, and we're gonna land on, so basically the U channel will give you the S channel plus some corrections, okay, that as I said, we have under control. So we're gonna basically land on this guy plus correction of order Tm over the cutoff. Okay. And and then we are here. Okay, so here I used unitarity again to replace the discontinuity, now that it's a function of T, with the this matrix element. And now, okay, now the second challenge is okay, unitarity is not there anymore. How do we do? Okay, so there is another inequality that we can use here, which is also very simple, and it's what I'm going to call a Cauchy-Schwarz inequality. Oh, sorry, that's not how.
Why do you say that the unitarity is not the positivity?
Positivity is not there. Unitarity works. You cannot say, "Oh, this is positive." Yeah, sorry, maybe I missed. Okay, so we can apply this Cauchy-Schwarz inequality, which just tells you that 3, 4, and dagger M is 1, 2, and we're almost done. It's smaller or equal to the forward one. And 1, 2. Okay, so this is basically saying that non-forward is always bounded by forward. Word. Okay, so this is basically x times y is smaller than x squared, y squared, but then if you take 3, 4, 3, 4, then you can just rotate because the S matrix is invariant under rotation, okay? Okay, so this is an inequality that is always valid, and we can apply it to this guy, the last line. And what we get is basically that now we don't have this larger than 0 anymore, but we have that this is smaller than something, and this something is the amplitude in the forward limit. Okay, this, let me maybe write it explicitly, is ds over 2 pi I, and then this guy is smaller than lambda 1, 2, and dagger m 1, 2, plus the other piece. And I expanded also the propagator, the denominator, okay? And this is just equal to the arc at t equals 0. So we have that the arc at finite t is smaller than the arc at t equals 0, And this gives us some new inequalities. And this is up to these corrections, but these corrections we can compute and we can check that they are small. Okay, so what does this imply for our bounds? Let's go back to this. So now what we need is the arcs when t is much larger than m squared. And this happened to take this form, lambda 3 to the 6, another function here that I'm not going to write explicitly. And the constraint that now we're going to impose is that basically this guy is smaller than this guy. Okay, a finite t is smaller than t equals 0. So this is like, let's say, a, and there's an absolute value. A of lambda 1, lambda 2 at finite t is smaller than a lambda 1, lambda 2 at t equals 0. And here you can immediately see a bit of some tension for the following reason. Now we have t larger than m, but this guy is larger than that one. And one scales with m and one scales with t. So like immediately you see that this is going to give you some constraints. Now, if you were able to take t all the way to infinity, which we cannot, but let's assume for a second that we could, then the only solution to this inequality is g equals 0. And g equals 0 is basically gives you 3 lines, because they have different values of the helicities that you can play with. And these 3 lines look like this. There is one like this, there is one like this, and there is one like this. The 3 lines don't have any, they don't superpose in any point. Okay, so there's no, so basically, let me rephrase this. So each line satisfies a positivity constraint. So if there's no point that is satisfied by all of them, then this theory is excluded. Okay, there is no common point between these 3 lines. They don't intersect.
So the 3 lines come from the 2 constraints coming, one from a of t absolute value less than a of 0, and the other t square t much bigger than m squared.
Okay, no, so the 3 lines come from g equals 0, basically. Okay, which comes from this. Okay, if you plug in the 2 expression, you're going to find that g must be much smaller than f.
So that constraint is enough to put g equals 0. I mean, it is not needed t much bigger than m squared to have the g equals 0.
Okay, so let me rephrase. Okay, if I take t all the way to infinity, the only way to satisfy this is g equals 0.
I see.
G equals 0, the solution of g equals 0 is these 3 lines.
I see.
The intersection is excluded. Now, in general, we cannot take t equal to infinity because this puts us outside of the EFT. So instead, what we're going to do is the following. We're going to take t of the order, like, let's say, 0.1, or like close to the cutoff. This gives us some regions. And at that point, we can like play with the mass and see when this region disappears. And this game we can play. We can change like t's or like this, and then this gives you a region that is consistent with positivity. And then you can start pushing the mass up, and at some point this region shrinks. And when it's completely gone, you're like, okay, this is the cutoff. And if you play this game, you get the following bound, that the cutoff is basically order 10 the mass of the graviton. Okay, so this is just like a bit of a game with these inequalities, trying to like play with t, how close you can be to the cutoff, and what is the allowed region. Since I'm going a bit over time, I'm gonna.
So you lose a lot of. It's a very restricted. Is a very restricted portion of the space that you can make prediction, where you can make prediction, because I mean
exactly. Let me tell you now what this imply for our original question. Okay, so this is more, we have a more precise. It's like order. It's like 30 m with some. We have more precise, but this is basically the.
I see.
Okay, so that is order 10 of the mass. What does it mean? Let's go back to our original question, which is like, where does the cutoff of the theory lies? And what we found is that the cutoff is like smaller order 10 the mass. So this means that if you're like at any distance smaller than 1/10 of the size of the universe, then you need to introduce new physics. Okay? So literally, this is something like, oops, didn't mean to erase that. Okay? So this means that like somehow here there is a 1 over lambda, and you can use your effective theory only from the Hubble scale to like 1/10 of that. And at that scale, there's no like structures in the universe that are that big that can like give you some like strong couples, Weissstein mechanisms, or anything like that that can save you. And at that point, I mean, if you are like these large scales and then you have to introduce a new theory, then it's not a very useful theory. That's our basically the final. Yeah. Okay.
So this massive theory
It's not very good.
is not very good.
Yeah, I think the punchline is that, I mean, a theory of a spin 2, it's fine in general. But if you want to apply it to gravity, for the particular case of gravity, when the mass is so tiny, and then this just tells you like new physics has to come very close to this mass. Okay, and this is like something that is like a general property of higher spins. You cannot have a stable higher spin in isolation. You have to add something that appears to kind of like save. And we know that, you know, the examples, the consistent examples we know, they always come in like a tower or something like this. Okay, so this would be consistent with that idea.
The tower of that was done many years ago, that they were saying that strings are needed,
for example,
to
like
make
higher spin states in
completion.
theory, some like AK modes, if you have some, you know, some higher dimensions, compactified, some, even like in QCD, when you have a resonance, it doesn't appear alone, it appears with like a tower somehow. They will never really appear in isolation. That doesn't really apply, this argument doesn't really apply to resonances, but in general, we see that this is all the examples we know satisfy this, and one way of seeing why this is the case is this positivity bound. Okay, so let me just conclude real quick. So what we found is that the cutoff must be very close to the mass of the state. We have like very good control over the correction, so we checked that our error is like smaller than 10%. We didn't want this to be too good of a bound for the following reason, that if you're too close to the Hubble scale, at some point you're gonna start feeling that you're not in flat spacetime anymore. Okay, so you would start feeling that we are in the sitter, and then the amplitudes will have to be modified. So we're happy with this order 10. Okay, so that our assumption that we're working with Lorentz invariant, like in flat space, are still valid. So, but this can definitely be improved to like have an optimal bound. I'm sure like numerics can be used, but for our purpose, that was not necessary. Another interesting thing that you can notice is that this bound is independent of M Planck, which it's a bit surprising because if you're used to positivity bounds in gravity, they usually are dependent on M Planck. And the reason is that this ratio here, so where is M Planck? M Planck is hidden in this lambda 3. Okay, this was a function of M and M Planck. So like if you take the ratio of these two, M Planck cancels out. So this is like, it's not even like, oh, if you turn off gravity, things like, it's really a property of this theory. As soon as you turn on, if you go back to the original drawing that I was making of the, you know, UV and IR, as soon as you turn on the mass, basically you're almost like always kicked out of the allowed EFT. And you're immediately forced, like you go from like, I don't know how many order of magnitudes gravity, I think it's like 60 order of magnitudes from the Hubble scale all the way down to the Planck scale. You go from there to like 1 order of magnitude.
Wow.
So this really dramatic change as soon as you turn on the mass. It's not like a tiny deformation. It's really like completely different theory.
I mean, it could be a very tiny mass and change everything.
It changes everything. You go from 60 order of magnitude effective theory to 1. So this is like there's no smooth limit when you turn off a mass, which is the case for spin 1, but not for spin 2. For spin 2, there's like a really discontinuity between mass or no mass. And yeah, so I think there's probably like more application. This bound can be optimized for, this is very general. It applies to any stable massive spin 2. So if you have like other example of spin 2, it might be interesting to like optimize this bound and see exactly how much it is or when you need to introduce some new physics. And also, I think it's like the trick that we found is could be easily applied to higher spins, because higher spins make it even harder, because you have now 2s+1 combination of helicities, you have 4 of them, it's a mess, and you have a lot of amplitudes, and they tend to be even more constrained the higher the spin is. And yeah, and this trick with crossing can be applied to any spin. So this probably has there's a way to reuse these techniques to go to higher spin. So probably future direction.
When you go to higher spin, I mean,
yes,
following what you did, I mean, without doing the X matrix that you wrote before, doing the same procedure, I mean, putting a constraint at t equals 0, but without doing the crossing through the full Wigner functions of the X matrix.
Yeah. So at t equals 0, you don't have this crossing problem, so you can just like do immediately crossing and everything is fine. And so Brando and other collaborators have looked at the spin 3 explicitly at some point, and already at t equals 0 is mostly excluded. So like these constraints are very strong. But here we find that if you move away from t equals 0, you get better constraints. We were able to go from
so I will kindly ask you to go to the slide where the analogy to higher spin could be more evident. I mean,
okay, let me go back here. Okay, so here, so at t equals 0, nothing changes. Literally, you go here and then it's positive and that's it.
Yes.
The challenge is what? The challenge is writing an effective theory for a higher spin, which contains all the possible coefficients, and then it's a large phase space of all of those. So like you have to play around with all these constraints. There's a lot of them because you have, here, sorry, let me go back. So here the constraints F positive, lambda 1 runs from -2 to 2. If you have higher spins, it's going to be a lot of constraints with a lot of parameters. So it's a bit more complicated to kind of like analyze all this space. You cannot do it by hand as simply as we did here, but nothing changes. If you, and yeah, there is a paper by Brando, Francesco Scarlata, Francesco Riva, I think Javi Serra, to be checked, that they do that. The claim is that you find even stronger constraint if you go finite t, but finite t, you have this problem with crossing, but the same technique that we use here can be applied to higher speed. So in principle.
And I mean, also if I construct the amplitude, for instance, based on little group arguments, on the covariance of the little group, so without thinking of a Lagrangian, about a Lagrangian, I mean, I can follow the same steps.
Oh yeah. I mean, that's what I did when I was computing these amplitudes. So like I just constructed, I don't know, every possible contraction of this polarization tensors, and then every possible contact term. Basically, it's like a game of writing down every contact term that is consistent with little group, etc. Then you look at these amplitudes explicitly. You try to have a soft behavior at high energies. So if you just write down an effective theory in a general one with the generic V up to some number of derivatives, you will get something like s to the 10 or something like that. And then you can try playing with this coefficient to try to tune it down to s cube. That's how it works for the RGT. In general, I think, I don't know, this has probably like a 2s minus 1 or something like that. Like there's like the higher the spin, the higher the energy. This is the spin, sorry. Spin. There's probably a behavior, a minimum behavior that you can get. And then once you have that, you can start playing in this space of positivity, but the number of free parameters is going to become larger and larger the higher you go. Something that would be very nice is to see how explicitly some, I don't know, some theories with towers end up evading these bounds. Like how does like a string theory, like does the next state with the higher spin enter at the right time to satisfy the positivity bound of the one before, and then you have another positivity bound, and then the next one will satisfy it, and how explicitly this construction is saved from these bounds, because it must be, because it should be consistent with these principles.
I mean, the constraints would fix the way in which the tower of spins appears, no?
Somehow.
Or I can also, I mean, for instance, in LHCb, there are many resonances of higher spin. So this could also tell me about, I mean, the rate, the decay rate, and
yeah. So resonances are a bit of a different story, because like what I'm assuming here is that my so I'm computing amplitudes like this, I don't know, stuff like that. So like my massive gravitons are asymptotic states. So if you have like, if you want to compute scattering of resonances, this becomes more.
I see. Yes.
Because like it's not really an asymptotic state, but for any theory with some, I mean, it can be an approximation. We can say like, okay, we approximate the asymptotic state. What does it imply for my tower, and how does my tower satisfy? And then basically you can start with like, let's say the lowest spin is like spin 2. I compute the amplitude, I get a bound. How does adding the spin 3 evades the bound? It makes it work. And then you like, okay, spin 3, then I get a new bound, and then spin 4 has to appear, and then how explicitly this tower makes this whole story work, because it should somehow, right? But I mean, I don't know. I'm not working on this right now, and I think it's an interesting
problem.
It's an interesting problem, yeah. Yeah.
Okay, thank you.
It's about what I wanted to tell you, so I'm happy to get.
Okay, thank you so much for your dedication and really your effort to explain us in a very clear way. Thank you so much. Really, we appreciate it so much. So, question for Giulia, for Dr. Isabella, Giulia, our friend.
Okay, so feel free to.
There's a question from Christian.
Hi.
Why I cannot see nothing?
Thank you for your talk. I have just one question. I don't understand what do you mean by the RGT gravity?
Okay. Let me go back all the way. Here. So DRGT, okay, let me just rephrase. So you see, like I can add like a mass weighted potential to my Lagrangian, okay? And then I can compute amplitude. This is like V will contain stuff like, I don't know, now I'm inventing, like C1, H, contracted in different ways. I can have like, I don't know, you can contract these two indices and these other two, or I can have like a C2 with differently contracted stuff. I can have a 3-point function. I can write the most general up to 4 H's, okay? Most general potential. And then I compute the amplitudes for this guy, okay? And then I just try that in the large energy limit, when I take S large in my amplitudes, I want this to go high as much as S cubed, not higher than that. And that fixes some of these coefficients. Okay, now I don't have it written down exactly, but you get something like, I don't know, C1 plus C2 equal to 0. Like, you have to fix all these coefficients, and you end up with only two free coefficients, C3 and D5. And this is what we call DRGD gravity. It's the best behaved massive gravity with this potential.
Okay, I remember that I read in a paper that DRGT gravity is a ghost-free gravity. Is that correct?
Yeah, so this is another way to find this C3 and D5 is to look at this how ghosts appear, and this is the only combination that allows you to get rid of all of them, of shell. Another way to construct it, which I prefer, is like you go on shell and you just ask for the softest, high energy behavior, and this give you the same answer. This also goes free. Yeah.
Okay, but could the ghost-free imply violation of unitarity or not?
So if it's ghost free, I would say there's no, in principle, any problem with unitarity to start with. What we find is that if you impose unitarity at the level of dispersion relations and these contours in the complex plane, then you actually get constraints on this. But yeah.
Okay, I see. Thank you.
No problem.
Other question for Giulia?
Yeah, one question.
Yes.
I was wondering what's going on if unitarity is not assumed. I mean, do those positivity bounds also hold for a theory describing an open system, or?
Ooh. Okay, so the argument I did definitely doesn't work if you get rid of unitarity, because I mean, the step to write the discontinuity in terms of this matrix element which is positive, then you cannot do it. So the answer is no. You have to consider a closed system and the full complete system. I don't know if any attempt has been made on like what constraints an open system which is part of a closed system that is unitary. Like what constraint does impose on that? This I don't know. I think people have been thinking about that, but I don't have any. Yeah, getting rid of unitarity hurts.
Okay.
I don't know if you had in mind something more precise.
And actually, I mean, in this business of cosmological correlators, where I mean, also there the cosmological optical theorem has been found. Constraints
Exactly.
can be set. Positivity constraints can be set. Probably, of course, technically in a different way, but in principle.
An interesting question is like if you start getting rid of any of those assumptions that I made, like, do you have anything left? And the answer is like, as far as I understand, not much, because like Lorentz invariance, people tried to put bounds without Lorentz invariance, but there was a paper last semester where they looked at like a UV complete example of a theory with broken Lorentz invariance. I think it was like I don't remember exactly the details, but the point is like they have like branch cuts at tree level, they have like crossing is violated, like a lot of those, like everything breaks down. So like exactly what's happening and how to apply things is I think it's an interesting question, but I don't think we understand it very much, like getting rid of any of those assumptions.
Any other question for Giulia? And about the completion of three-level amplitudes by tower of spin of higher spin, that would imply essentially string theory. I mean, since there is it is an effective field theory, why one is made sure that from the tree level has the prescription to complete the theory at all scales.
You're asking like where the loops come in, like
Why the loops cannot help in this sense?
okay, so let me comment on loops. So here I basically mentioned that okay, we're gonna take the contribution from the branch cut is basically starts where I start my contour. But in general, I'm gonna have like some, you're gonna start having a branch cut here as soon as I would say I think it's like 4m squared. No, as soon as you get into at energies larger than 4m squared, then you have this type of loops that contribute. Okay, so this will give you an imaginary part. This we are ignoring. We're ignoring these contributions. Okay, so we're basically only taking a tree level in the EFT, but there's a reason for that. Like, so you can, in principle, add those contributions in your branch cut. So add some corrections there that we know, like it's like, okay, the branch cut contains new physics, but it also contains loops of what we know already. And this is something that like Brando and collaborators have a paper on that. That was their first paper on massive gravity. And they show that basically if you include those, the bound gets stronger. So loops actually like make it even better for us. And these loops actually imply that the UV completion is weakly coupled. They imply that this guy here must be below the strong coupling scale. Because in general, you could also have a UV completion that enters later. You have like some strongly coupled dynamics, and then at some point you have new physics. But adding these loops shows you that this has to lie actually like, above the strong coupling scale. That's what we see from loops. So in general, loops seem to make it like even a better case for these positivity constraints. So that's why we ignore them.
So the loops put in evidence that you really don't need strings to save the unitarity of the. I mean,
you need new physics. The loops tell you that the new physics will appear before you hit the strong coupling scale. So before everything is going to be weakly coupled. Your UV completion is going to be weakly coupled. You're just going to add some new states to your spectrum. You can keep doing perturbation theory all along. This is what find the loops tell you. So in a sense, like they tell us that we can use our tree level amplitude safely within this little circle. We don't need to, like a loop will just give little corrections. It's never going to become large and break down perturbation theory.
So I mean, with loops, one is made sure that can extend the domain of validity until when perturbation theory is possible to apply.
Exactly. And this is gonna be valid all the way to the new physics scale. It's gonna appear here. We can do like safely perturbation theory. We could add loops, but those are gonna be small all the way to lambda. You don't have to worry about them. We have some estimate, and they actually make the bounds better even if you add them. So we ignore them. Yeah, they have a discussion on this.
And I mean, an amplitude with loops with higher spin would be useful to make
so you want to put, I see.
better constraints with the higher spin. About
so you want to put higher spin inside?
Yeah.
Do you want to put the higher spin inside the loop? Yes, exactly. This is exactly the type of diagram that would contribute to this branch cut. Because as soon as if you take lambda of the order of some big M, which is the mass of the higher spin, as soon as you got energy above that, then you have to introduce this type of diagrams, and these will give you the discontinuity precisely. Those are the ones that save you unitarity and everything. This is the type of diagram that actually will contribute to this branch cut. Sorry, this is getting a bit messy.
And this would constrain with what kind of configuration of higher spin one would need to be everything consistent, or
so as soon as you start introducing new states, then you have a particular UV completion, right? So what you can try is, yeah, I can introduce that, and then now I assume that my EFT goes all the way to here. I have a larger radius, and then I can do positivity again and see what this implies for when the next cutoff is. But as soon as you add a new state, then you're beyond the EFT that we had, and then you can check that, yeah, it work out, but you haven't made a choice of what UV completion. The idea here is to be really like, I have no idea what's happening above. I don't know which new states will appear. I just like this bounds just on the stable state that I have.
So do you think it is worth to consider those contribution in higher spin?
I mean, it can be an interesting exercise. Like, okay, I started with my only spin 2. This is the bound I get. And then I introduce in my spectrum a spin 3. I start having like this type of diagrams. Or even like at tree level, you have like this with a massive guy, stuff like that. What is the cutoff of this new theory? What are the positivity bounds on this new theory? Is this larger? Can I make a larger circle and be safe in there? And then you can ask, okay, what is the positivity constraints again? And you can add another state, higher spin again, and then see. And also like as soon as you introduce a new state, then you have like another amplitude, which is like all heavy guys. And then there's a bound on that. So the more states you introduce, the more bounds you have, and it's a non-trivial problem for sure. But I think it's yeah.
Because I mean, in the early days of the standard model, a way to obtain the interaction was made by three-level unitarity.
Yeah.
But of course, I mean, this is an approach where loop unitarity can provide the shape of the interaction of, for instance, higher spins. No?
Yeah, I don't think we have something to say about that. I mean, the fact that the UV completion is weakly coupled, then I would say in general we expect tree level to dominate. But I'm not sure.
I mean, in principle, loop should be negligible.
In principle, I mean, as in the IR, what we did for sure, then adding new particles to the spectrum, then I would say so. I think you're still dominated. Since it's weakly coupled, you're still dominated by tree level. I mean, they give you corrections. I'm not saying loop don't matter, but they are not, yeah, they're not so important.
I see.
In terms of size of the bound. That's what we observe. But I haven't thought much about like adding new states and how this would enter, how the calculation would go, to be honest. Yeah.
Okay. Okay. There is Daniel. What role? That I can. What role does 1 over s minus 2m squared to the cube play in the analysis? For example, why that denominator and not the square, or onto the 4 or power to the 4?
Okay, so the most basic example where positivity was applied for the first time which maybe you have seen before. It's just like a simple scalar with some interaction like this, okay? And this guy goes like S squared, okay? Let's say we want to bound him. So we need to, I said that we need to divide, this is the amplitude, okay? You want the amplitude to be divided at least by S squared in order to throw away the contour at infinity, okay? So S to the n, where n must be larger than or equal than 2. Now, if you put 2, your circle, okay, let's say if you put n equal 2, then your integral is something like, you just integrate over alpha. There's no poles in the small circle. And then this will just give you 0, okay? Let me just remind you. There's like a small circle, there's the branch cuts, and then there's a large circle. So you see the integral over a small circle is basically a sum over all the poles and branch cuts inside the circle. But if you put s equal 2, there's no poles, there's nothing. So the answer is 0. So 2 doesn't work. 3, if you put pick n equals 3, then you get 1 over s behavior. And that gives you precisely a pole at s equals 0. And so when you do this integral, you get something proportional to alpha, and then you can bound alpha. Here is a similar story. If you want to bound higher powers, so if you have some d mu phi to the 6, let's assume this is allowed, this gives you s cube. And then if you want to target beta, then you have to go to n equal 4. So depending on which Wilson coefficient you want to target, then you're going to choose the power of your denominator so that you still have a contribution. That's here. And then we played around, and that's what was useful for us, this choice that was also cross-symmetric. Yeah. I don't know, does this answer the question?
Yes, I mean, it is not just to throw away the big circle, but also the convergence of the small circle, which is provided by the EFT and the corresponding Wilson coefficient of the higher dimensional operators.
Yeah, it's a trade-off between the two. You want to be able to throw away the infinity, but at the same time, you want to be able to target whatever you have in the EFT. So you kind of have to play around with these powers and these substructures.
Okay,
Yeah.
Okay, I don't see any more questions. Really, Giulia, thank you so much for your great work and your nice job. I mean, we really explain us many interesting things, and I hope we can stay in touch and still have discussions. If you can share your notes with us, it would be
Yeah, I can
great.
send you those. There's not much written there, but I can send them to you.
Or if you have slides similar to what you wrote, and you can
Okay.
you can
I'm
send
not,
us.
I'll check.
Okay, as you wish.
Okay, let's see. I can send you something.
Okay.
Okay.
Thank you
Thank
so
you very
much.
Have a good rest of the day.
Yeah, you too. All the best. Ciao,
Okay.
grazie.
Bye. Ciao.
Many thanks.
Ciao.
Grazie.